Okay, starting today we will see some designs using medium scale and large scale integrated circuits. First we will look at the combinational circuits and then include the sequential part of it. I have mentioned this several times earlier in the course. Ultimately success of the design depends on how efficiently we are able to make a design for a given set of specifications in terms of the size, in terms of the power consumption, or in terms of the costs. So if you want to have a design, of course the types of design, the sizes of the designs we have seen so far in the class are small. So a gate based approach is justifiable. But when the circuits become larger and larger, systems become larger and larger, it becomes extremely, very large, extensive, in order to have a large number of gates. So with the large number of gates come things like reliability problems, interconnectivity between gates. External interconnection is unreliable compared to the integrated circuits. Of course you can make a very sturdy and rugged printed circuit boards, but still a circuit which is fabricated as an integrated circuit will have much more reliability in terms of the failure compared to a circuit which you put together outside. Then the size. The size of an integrated circuit package, as you see it, so there has to be a minimum size of the package for you to handle it, so that you can put it in a board and you can wire it. So you cannot make a even though we are talking of micron technology and sub-micron technology, that means we are talking about dimensions of transistors being in the order of microns and sub-microns, we cannot handle them. If I give you a small piece of transistor fabricated using a micron technology, how will you handle it? You cannot. So you need to put it in a package, and the package has to be hermetically sealed for protection from environment, but you need to connect it properly. So in an IC, the extra circuit, the cost of the extra circuit that you put in a chip is not proportional to the final cost of the circuit. That means there is a minimum cost in the fabrication process in terms of the infrastructure, in terms of the technology, the clean rooms, lithographic techniques, in terms of packaging, in terms of reliability, in terms of testing. This is a very high component of the total cost of an IC. So give an example, if a circuit with about 10 gates, when I say 10 gate circuit, as I mentioned this again several times earlier, 10 gates does not mean there are 10 gates inside. A circuit whose performance is equivalent to the performance of 10 gates is sold, let us say, for 10 rupees. It does not mean that I make a circuit for 100 gates with 100 gates using the same technology, same processing, same packaging. It does not mean it will cost 100 rupees. That is, the complexity of the cost of the circuit is not proportional to the complexity of the circuit. There is an incremental cost increase, a small increase in the cost because of the extra design effort, but that's it. I don't think you will have to account for the chemicals that will be used extra in the process. The wafer size is, as I said, the same. You cannot handle less than that. The package size may be same. The packaging technology may be same. So instead of 10 rupees, maybe you can sell it at 12 rupees. So it's a dramatic, it is not a insignificant factor we are talking about here. So as the circuit becomes larger and larger, the cost per function, if you want to define the cost per function, it drastically reduces. Take of memory chips. Why are we able to get now memory chips in computers with a huge capacity for a much smaller price? Because it's one IC we are able to get it. Suppose a memory of a particular size, let us say 1 kilobytes, costs a certain amount. Earlier, if you wanted to make 64 kilobytes, you need to buy 64 of those memory chips. Today, if you can make a 64 byte memory, the cost will not be 64 times what it was, but of course maybe twice or even let us say 5 times. I don't know, it depends on the technology, the design effort, the testing effort, and the extra changes you have to make in the processing steps. But you get the point. It is not 64 times, it is maybe at the most 3-4 times. That accounts for a very drastic reduction in the cost of electronic circuits today. We have computers which are always costing less than what it was earlier for a given performance. This is probably only one of the very few areas of human activity where the cost goes down. Any other area, be it agriculture, be it textiles, be it whatever, manufacture, the cost will be proportional to the effort, and it costs also you have to take into account inflation and everything. But here I can buy today an electronics hardware which costs less from last year for the same function, or for a given cost circuit this year I can buy much more complex circuit with much better performance compared to what I could have bought for the same price last year. That is because of the advance in technology. So why am I saying all this? Because now the time has come for us to study from gate approach. Even though the gate approach is required for us to design, to understand the problem, to minimize and then see how it functions. Functional understanding of the problem is very important. Functional understanding of the design is very important. But I would rather use ICs which are larger, because there are few of them compared to a large number of gates, very few of them for a given performance, given specs, given set of specifications. If I can decide using 5 ICs instead of 100 ICs, I would definitely prefer it for the reasons I mentioned earlier, the cost, the size that is going to occupy in the PCB. Finally, when you make a chip, it has to go as a board which gets into your computer and other electronic devices and appliances, especially when it is space applications and things like that. The size is of major importance. So I can put in a smaller area the performance of the circuit function system compared to if I had to do the whole thing using functions of less complexity. So size reduction, cost reduction already talked about. Power reduction, because power is not again proportional to function. Power also, there is lots of power which is wasted in switching activity, in distribution of the power rails along the IC. Power of course is proportional to function to a certain extent, and the switching activity to a certain extent. But there is also some power consumption, saving in power consumption when number of ICs is small. For example, when the large number of ICs, they get all switched on and switched off whether they are used or not. So some of those can be, they may be a waste of power dissipation. And finally, and most importantly, is the reliability. As I said earlier, even today, what I said was, if I can connect something together with a reliable connection which is very, very tight, practical probability of failure is very, very small, remote, almost nil. That is assured only in the processing, because it's a chemical processing and all other processing, lithography, the implantation techniques, and all those technologies which you are going to study later on in other courses. It is not a technology where you put together, it's not a mechanical technology where you put and fasten things together. Sometimes the thing gets coupling goes, or a screw gets weakened, or even in electronic circuitry where we put external circuits, ICs, and connect them together by either wires or by printed circuit board channels. Here it is all bonded together as the circuit is made, as the circuit is fabricated. So that means if once it is tested and IC is tested for function, very, very remote possibility, there is a very, very remote possibility that it will fail. Fails occasionally because of a condition which was not tested has occurred in the operation of the circuit, or it could be a radiation or some other aspect which has not been considered earlier. Otherwise, you connect a wrong power supply and then pump extra current, much more than what it can handle. These are not, radiation and an extra power dissipation, driving it with voltages much higher than what you have designed the circuit for. These are not considered as failure because of the circuit. Occasionally there may be a circuit failure because of a condition which has not been tested earlier for that condition, not tested, so assume that it will work for that condition. That when the condition really happened, I don't know if you know, but I don't know whether we are really following such things. A few years ago, you might have been in high school at that time. There was a major problem on Pentium chips, because you see they go through Pentium is a microprocessor by Intel, which is used in all these computers now. Pentium processors, and they go through a very elaborate design procedure and testing procedure, and they suddenly reported problems, failure, or circuit didn't work. It was found out that a rare combination of certain functions which is not tested had occurred and that appeared that it was not a very infrequent thing. It could occur very frequently in some computation. So what Intel did was to recall all those computers, all those chips, and then they made the corrections in their design and reissued those. So, but it is very rare, these things. Otherwise, what I am trying to say is the reliability is very, very high when you do integrated circuit rather than connecting circuits discretely outside the chip. Because of these reasons, we have to go in for ICs which can do more than a simple gate function. But what is the price you pay for it? The price you pay for is we can never optimize. For example, if I give you a circuit problem, a design problem using combinational or even sequential logic, you will always optimize for the minimum number of gates using corner maps and then say this is the best possible solution. But then here I don't have gates. I may have come up with a gate solution, but where are those gates? I am asking you to connect something which is not gate. There are components. These components will have equivalent gate functions, but they are not the gates. For example, I cannot get, suppose I require about half a dozen AND gates, a few OR gates and inverters. I may have an IC which may not exactly have those combinations. So I should be able to map on the given hardware my function. My function that I want to implement, I should be able to map. Of course, when I do the mapping, I will do it most efficient way possible, but it will not be the efficient way in terms of the gate count. See, I may be spending more functional equivalents of gates. So I will call it loosely more gates. I may end up using more gates to implement a function compared to what I would have done if I had all the gates available. But that is the price you pay, but it doesn't matter because I am now using smaller number of ICs. It's going to be cost effective, it's going to be high speed, is going to be also less power, and a small area. What does it matter? In fact, if I'm going to use all of them, all the parameters I'm interested in monitoring are going to be better in my design, how does it matter if you don't use the minimum number of gates? It doesn't matter. So the mapping of the hardware, mapping of the given problem when the hardware is available, may not be the most efficient way of doing it, but we'll have to do it by experience. There are certain times, sometimes there are some tools or procedures available for this, but not always. Most of the time it is experience. What they call it heuristic, intuitive. It's an intuitive design. Okay, this is what is required, this is what the available component, this is the best way to connect it. As I said, certain times, sometimes there is a procedure, many times there may not be procedures, but still you can, once you have an experience of designing, you'll have a feel for it. If you connect it this way, you'll get the better performance compared to if you connect it this way. Or sometimes you may have to do trial and error to find the best possible solution to that. That's also fine with us. So this approach is called intuitive approach, or people even call it heuristic approach. I don't know whether you heard of this term, heuristic approach. Rather than a fixed procedure. Of course, procedure may be there, but it may not be the efficient procedure, and always procedures may not be there. For simpler ICs, there may be procedures. Again, as you go higher and higher into ICs, if you have a gate count of 1000 and above, or 1000 gate function, my complexity of the circuit design is also about 1000 gates. I am trying to map this functional requirement into the hardware available. I have a hardware which is 1000 gate equivalent, and I have a function which is 1000 gate equivalent. I have to map it. I have to do a best possible way. Of course, I can't do it manually. I have to depend on software, and the software limitation of the software is the software designer's limitation. Whatever he or she knows about it, and that person may not be the person who is knowledgeable in the particular application you are doing. So there may be a generalized efficient way you may get, but when you do it yourself by hand, you may probably do it better. But these are some of the problems, but these problems are very, very insignificant compared to the advantages in terms of the cost saving, power saving, improvement performance, and size saving. So with this little introduction, we will talk about first combinational logic. Combinational logic design. Later on we will do sequential. Using first MSI we will use, and also we will later see SSIs. LSI. Medium scale integrated and large scale integrated circuits. So it's always possible to map. You see, everything is, as I said earlier several times, everything is gates. Whether it's a full adder, a 4-bit adder, whether it's a decoder, whether it is a priority encoder, what is that we talked about? The parity checker, code converter. It's all gates, and what we have to optimize also gates. So this is sort of a common sense. It tells us there is these gates which are required, and these gates which are available in this hardware piece I am giving you. I am giving you a hardware piece in which there are gate functional equivalents, and I am trying to design a circuit with gate functional equivalents. So how best can I map it? And it's not always that it's possible, the best possible way may not be available to you, because inputs and outputs should be available. You should be able to feed in things, you must be able to take them out. So you may come up with the best scheme, but it may not be possible because there is no input pin for that. You can't break open an IC and put a signal inside that. So you'll have to work with the inputs and outputs being available to you. Okay, so first we will talk about MSIs, and the first MSI we will talk about will be, all of you have been asking me for this for so many days, what? Multiplexers. You all thought that I am going to finish my course without teaching you multiplexers. And then we will also talk about decoders, and then we will go to LSI, and we will talk about proms and programmable logic arrays, and then probably go to sequential circuit with counters and shift register, which are already familiar, but then how to use them in a design. Okay. Now, what is a multiplexer? Basically, multiplexer, as the name suggests, is multiplexes. That means I have several inputs and you have to select one of them. It's a selector. Multiplexer is nothing but a selector. So if I have a hardware which I call multiplexer, for MUX for short, they call it MUX. Now I have several inputs. Let us say I0, I1, I2, I3 are these 3 inputs, and at any given time I want one of these outputs. I want F to be either I0 or I1 or I2 or I3 based on my requirement. So I need to connect one of these inputs to the output as required. That means I need some control. When do I connect I3? When do I connect I2? So that means I need signals which are called control signals or selectors. And number of selectors will be based on the number of inputs. Depends on the number of inputs. If you have 4 inputs and one of them has to be output, how many selectors do I need? 2, because 2 selectors can have 4 combinations, and each one of those combinations can connect the given input to the output. So I'll call these selectors S1 and S0. S1 and S0 are the selector signals. I0, I1, I2, I3 are the input signals, and F is the output signal. So the function description of the multiplexer is F is I0, S1 bar, S0 bar, I0, S1 bar, S0, I1, S1, S0 bar, I2, S1, S2, I3. That means if I make both these inputs 0, 0, both these selector inputs 0, 0, F gets connected to I0. So it's a selection process. That's all. I have several signals coming into the input, and one of them has to be connected to the output. And which one should be connected depends on the combination of the S1 and S0. So if it is 0, 0, I0 will go through, 0, 1, I1 will go through, 1, 0, I2 will go through, 1, 1, I3 will go through. Can you think of an application for this type of circuit? Somebody said something here. Yeah, it's right. Telephone exchange. As an example, I have 4 lines and I have only one of the 4 subscribers and only one line is connected. This may be your local exchange and this may be my local exchange. There are 2 villages. Of course, I am making the problem too trivial, but just to give you an idea. So I have 4 subscribers in this town and 4 other subscribers in this town, and I need only one person can talk at a time. So I have only one line coming from this town to this town. So depending on which person is dialing, that person will have a code and that signal will go through. There in the other side we have what is known as the reverse of this operation. Naturally it will be called a demultiplexer. When you have a multiplexer, so I will have one input and 4 outputs, and which one is connected, it depends on the selection you make. This is an example of a selection. There are several occasions in digital signals, in digital system design, where there may be several signals and you may have to select one of those signals to be applied to a particular circuit. So there are several signals and only one of those you have to select to be applied to a particular circuit. Use a multiplexer. Now this is a very simple, this is a combination logic, isn't it? F is, so if I don't have this is available as an IC. I can go to the electronic store and buy this. Ask for a multiplexer. Of course you can't say give me a multiplexer, you have to tell him how many inputs and how many outputs. So it's called a 4-to-1 multiplexer. You don't have to tell how many selectors because it is fixed. You say 4-to-1, naturally the selector is 2. Or I can have 2-to-1. I can have a 2-to-1 mux. I can have 4-to-1 mux. I can have 8-to-1 mux. I can have 16-to-1 mux. Beyond this, even 16-to-1 sometimes will not be available. But beyond that, you have to make your own muxes. That is possible. Having a smaller mux, you can build a larger mux. You can mix, you can connect a tree of multiplexers to realize larger muxes. But then, even though it's available, if it's not available, you are only gates. Suppose you are a die-hard gate utilizer. I don't want anything other than gates. That's all I can use, and please don't give me a multiplexer. Can you build one? Of course, because this is the function, and you know how to implement this function. How many gates do you need for this? 4 AND gates with 3 inputs each, 1 OR gate with 4 inputs, and then I need to have 2 inverters for S1 and S0. So I can have, for example, F I am not showing all these connections, it will be just sort of clutter the drawing, you know what I mean. So for this gate, for example, I need to feed this. This is S1 with the inverter, this is S0 with an inverter. Then like that you can finish, you can complete the drawing. I am not showing it because it becomes a very messy affair on the board. But instead of buying these 4 gates, 3 input 4 AND gates with 3 inputs each, 2 inverters and 1 OR gate, which will be how many ICs? Because OR gate and AND gate will not exist in the same IC. Naturally, I need to buy 1 IC for this. AND gates, more than 1 AND gate can exist in 1 IC, but then generally it is 4 2 input gates or 3 input gates. So I may have to buy 2 of those. 2 3 input AND gates I need to buy. Combination, not 3 input AND gates. It's a package usually. Like an inverter doesn't come as single. I can't buy an inverter. I have to buy a 6 inverters. One package of inverter will consist of 6 inverters. One package of NAND gate will contain 2 input NAND gates will contain 4 of them. Quad package. Like this. Similarly, AND gates will come 2 inputs, 1 output, 4 of them in one package, but then there are 3 inputs, so I need to buy 2 of them. So 2 packages of 3 input AND gates, 1 package of OR gates, 4 input OR gates, 1 package of inverters I need. How many ICs? Total 4. Here it is 1. This is MSI. Gate function wise it is only how many? 1, 2, 3, 4, 5, but then you don't count like this. Inputs, 2 input, 1 output is considered as a gate function. So I may have to 1, 2, 3, 4, 5, add some more numbers for the inputs, more inputs and inverters, everything. So about 10 gate equivalent, approximately. Don't worry too much about these calculations. I am not going to ask you to find out the calculation equivalent AND gates for a gate function for a given function or anything like that. But about 10 gates put together in this one package, it does the same job with all the advantages I listed earlier in this lecture about the size being small and cost being small. Naturally, I will go for this rather than this, right? This is the concept of medium scale integrated circuit design. So now, having decided to go in for these muxes than gates, how do I use it in a design procedure? The same combination logic design which I will know how to do exactly optimized way, most efficient way, saving the number of gates, using corner maps. Provided we are asked to use only gates, now how am I going to modify my design procedure to do the same problem using multiplexers? Okay? So let us do a simple example of a adder, full adder. What do I mean? Sorry, I don't understand. 2 input full adder. Sorry, 1 bit full adder using mux. I'm going to design a mux using a mux, 1 bit full adder, and all of you know the truth table, hopefully. Maybe inputs, here is the carry, sum and carry out. Sum is 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 1. That right? Please tell me if I make a mistake in the truth table in a hurry. And the carry would be that right? Now let me draw the corner map for this, just to show you how it is going to be placed. Or I will draw it this way. some corner map carry out corner map. That's a little board interface here. Let me move this a little further. So quickly mapping this on this, it is 0, 1, 1, 0. Is that right? No. 1, 0, 1, 0, 0, 1. And on this it is 0, 0, 0, 1, 1, 1, is that right? This is the carry output, this one. Now, it is where your design, as I said, it's not the intuitive design, as I said, heuristic design. Of course, it's not all that. It's very sort of very straightforward problem. But later, as the complexity of the circuit becomes bigger and bigger, and also it's not this symmetrical, then we'll have more of thinking to do. But in this case, there is a thinking step, but the thinking step is very, very obvious and straightforward. So I need to make, I would like to use a 4-to-1 multiplexer. I need to select two of these variables as selectors. I have three variables, A, B, and Ci. Out of these, I need to select two of them as selector variables. And when these selector variables 0, 0, what should be given as Ci, so that the output is what is required according to the table. So what I am going to do is, I am going to use a 4-to-1 multiplexer. I0, I1, I2, I3. And I am going to get a sum out of this multiplexer. And the two selectors, I am going to use my two bits A and B. Now, when AB is 0, 0, you know that I0, S is equal to I0. Is that right? We know that from this equation, or from whatever here, when AB is 0, 0, which is S10 is 0, 0, output S is connected to I0. So if I make I0 what is required according to this corner map, then that will be implemented. So when AB is 0, 0, sum should be same as Ci. Sum should be 0 if Ci is 0, sum should be 1 if Ci is 1. So if I connect Ci to this, if Ci is 1, when AB is 0, 0, the output will be 1. When Ci is 0, when Ci is 0, output will be 0, sum will be 0 when AB is 0, 0. And when Ci is 1, when AB is 0, 0, sum will be 1. That's what it is. Mapping the hardware, mapping on the given hardware, our requirement, which is here. But what is so intuitive about it? Because I chose this A and B as the selector variables and found out that this is how it has been done this way. I can also do it some other way. Now, when AB is 0, 1, output will be 1 when Ci is 0 and 0 when Ci is 1. So I need to connect Ci bar. Likewise, for this 0, 1, 1, 0, Ci bar, and when AB is 1, 1, sum is 0 if CI is 0, sum is 1 if CI is 1, so I need to connect CI. Correct? So with a simple 4 to 1 max and only one gate for inverting CI, I can get my sum. Whereas if I had used this, I would have used two input exclusive OR gates. Correct? That is what is the efficiency about this. Coming to the carry, again there are 4 inputs, so I will use AB as the selectors, and this mux is a 4 to 1 mux. This and this are 4 to 1 muxes. Now in this output I will get carry. From this map I will do this. So I am now mapping onto this given hardware, namely 4 to 1 multiplexer. Is a hardware mapping, not mapping like drawing. The hardware mapping. On a given 4 to 1 max, the given Karnaugh map to get the function implemented. Now when AB is 0, 0, output is 0. There is no carry, irrespective of whether CI is 0 or CI is 1. So I put a 0 here. Carry is always 0 if AB is 0, 0. If AB is 0, 1, carry will be 1 if CI is 1. So I put CI here. Is 1, 0, again CI. And if AB is 1, 1, when whether CI is 0 or CI is 1, we have carry out. So carry out is independent of CI, it has always to be 1. So I need to connect a 1 here. So with 2 4 to 1 muxes, I got my full adder. And the beauty about the whole thing is, 4 to 1, I was just now telling you these things come as packages. 4 2 input AND gates come as a package. 4 2 input NAND gate comes as a package. 6 inverters come as a package. Likewise, 2 4 input multiplexers come as a single package. It means this, I can go and find a 4 input mux individually. When I go and buy a 4 to 1 mux, I will always get 2 in one package. That means in one IC package, I am getting a full adder, as against the number of gates we would have used in the other approach. That is what is called a MSI based design. So I will have this full adder, which is going to look like this. So 1 4, it's called a dual mux, dual 4 to 1 mux. Dual means 2 of them in 1. Dual mux. The first mux I will connect CI, second and the third I will connect CI bar. This is I0, I1, I2, I3 corresponding to the first mux. Sum. This is 1 4 to mux, 4 to 1 mux. We have another 4 to 1 mux here. This will be connected to 0, that means ground. We put 0 then inverted comma, that means a ground potential, 0 potential. And this is the 1 means it is the VCC, whether it is 5 volts or 3.3 volts, whatever is the operating voltage, that voltage will be given here. And the in between these two are connected to CI. For the second gate, second mux, these are the inputs, This is outputs and this is my carry out. And to the two selectors we connect the 2 bits A and B, which would be connected internally. I am not showing all internally because we are only having these things available to us. So I will connect A and B here. So internally this would be taken here, this will 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 go here, this will go here. Internal connections I cannot make, but it is there. So in a single 4 to 1 mux piece, single dual 4 to 1 mux, I am getting a full adder. So single chip solution of a full adder. So this tells you there are ICs available which are larger in functionally larger compared to the simple gates, and these will be used in design in combination logic. Even in sequential logic, the combination logic is the steering logic, is it not? Steering logic is combination logic. So we need combination logic, whether it's a combination logic design or a sequential logic design. So we use these ICs which are medium scale ICs which have several gate functions in it. The design becomes simpler, but a sort of an extra effort is required. It's an effort in terms of properly identifying the requirements of the chip. For example, how will you first of all decide even? If I didn't tell you, use mux. If you say use an MSI and get a 1 bit full adder, so you should know how to do it also. Because there are other ICs also you can do. I can get a decoder using other ICs also. So first thing, make a intelligent choice of the MSI. Look at these specifications of the circuit given, specifications of the requirement. Look at the capabilities of the hardware available. Try to make a match to the extent possible. And this is a very symmetric and straightforward case. So sometimes we may have to do a little extra sort of manipulation, and in that process we may end up with a less than efficient design, but it's worth it because we are going to reduce the total number of ICs. So this is only an example. You can try several other examples, because anything that you can do with a 4 variable Karnaugh map A, B, C, D, we have done earlier using gates. Now you can go ahead and do it using multiplexers. This is a 3 input Karnaugh map. The total of ABC, ABCI, even though I split it, it's a 3 input Karnaugh map. Suppose I give you a 4 input Karnaugh map. How will you do this? Using a 4 to 1 multiplexer. Or sometimes I may have to go for 8 input multiplexer, 8 to 1 multiplexer. So there is no need for me to give you separate homework. What you can do is, you can take any of the 3 variable Karnaugh map reduction or 4 variable Karnaugh map reduction and try to map them into muxes. First using 4 to 1 muxes, and if necessary sometime you can use 8 to 1 muxes. 8 to 1 muxes and 4 to 1 muxes. Of course we will do some more examples in the class, but there is no need for you to wait for me to give a proper formal homework assignment sheet. Whatever we have done earlier with gates, in principle we must be able to do it with multiplexers. So what we will do is next see some more circuits using muxes, and then also see what are the other ICs other than mux, which are medium scale integrated circuit ICs, which can be used for combination logic design.